Because
Yeah, yeah.
okay, okay.
I'll record it. Thank you. Thanks for the reminder.
All right. I'd like to warmly welcome everyone to my final candidature assessment, the CA3. My name is Alan, and current PhD candidate. My thesis title is the Machine Learning for the Nutrient Recovery Management for a Wastewater Circular Economy. I know that's a bit of a mouthful, but it's about improving the nutrient recovery processes for, in a new world where we have a lot of critical mineral challenges, a lot of fertilizer supply chain challenges, and so on. Um, it's been a very productive 3.5 years being in the candidature, having co-authored other papers, having published 6 papers, one in review at the moment. And I've published 2 review papers, 2 conceptual framework papers, one roadmap paper for the Australian country, as well as an original experimental research paper, which will be the final part of our presentation. So, what is the nutrient circular economy for a start? For those that are on the call that don't really have a lot of background into it, um, but recently, we're seeing throughout the world, a lot of countries and a lot of regions are now declaring phosphorus a critical mineral, besides lithium, cobalt, and nickel, and so on. There is now a renewed focus or a need to recover this, critical mineral that's used extensively across fertilizers. And during the pandemic, when the borders were locked down, fertilizer supply chains have been disrupted significantly. We're still feeling the effects of that today, um, as well as the need to recover nutrients from wastewater effluent, which is a cause of eutrophication that leads to unwanted marine life blooms, and that can have detrimental impacts on anything that's swimming in the water body, essentially. We're seeing at the same time the proliferation of AI. Think about your open AIs, your Geminis, your large language models like Meta's Llama, and so on. We're seeing a lot of industries invest hundreds of billions of dollars every year in the hopes that the AI would improve productivity outcomes, would automate a lot of the processes, and lead to significant economic benefits for societies. And we're currently seeing a cost of living crisis, and so you're well aware that grocery prices have gone up. So anything that you eat doesn't have to be just carrots; it can be a biscuit or a chip. Anything that requires something to be grown out of the ground and is consumed, that cost gets passed down. And so there are, of course, economic benefits, or at least downward supply-driven inflationary effects of adopting a more circular nutrient ecosystem. And so, for those that are not familiar with how our current wastewater economy works, you flush your human waste down the toilet through urinals, through toilets, your fecal matter. It goes through MBRs, aerobic processes to remove and absorb all the nutrients, and then it gets the nutrient levels down to a level where you can safely discharge it into the environment. And every year, we're flushing about 20 megatons of nitrogen and phosphorus down the toilet every year. We don't ever recover that. And the energy potential from wastewater is significant. Nearly about 160 million homes could be powered every year if we could, for example, install thermal pumps, heat pumps to recover the thermal energy from wastewater, or to tap into the biogas potential within sewage sludge processing plants. And of course, there are a variety of technology, resource recovery technologies available. We're very well familiar with membrane processes like ARA, FOMD, UF, and FMF. They're osmotic or physically driven separation processes that are good for separating out undesirable substances, reconcentrating waste streams into much more valuable nutrients, or even just to recover water. There are biological processes. You're using living micro or macroorganisms to absorb the nutrients and to decontaminate, wastewater streams, for example, through the use of CWs or constructed wetlands. And we've also got electrochemical processes. They can be combined with biological processes for hydrogen generation, for electrodeposition of valuable nutrients and other critical minerals and metals onto the electrodes, as well as TDI, IXM processes, and through the use of ED, especially, you're able to concentrate nutrients into desirable streams. Thermal is probably the most robust. There's HTR, HTC, and pyrolysis processes where you can produce biochar, hydrochar, syngases, and other valuable nutrient recoveries. And you've also got your evaporation and freeze concentration, which allows you to recover water and the urea if it's source separated urine. And lastly, chemical, it's our most mature technology approach, which is struvite precipitation, adjusting the urine to an appropriate pH level and dosing it with magnesium, as well as with ammonium stripper, where you're raising the pH level, I believe, to condense the gas into an ammonia that can be recovered. And of course, we're seeing price shocks just before the GFC and during the lockdowns in the pandemic. We're still feeling the price shocks to this day. This is why it's important to insulate our supply chains for as much as possible to reduce our reliance on international, phosphorus supply chains. It's also, the same thing with, our reliance on international oil, heavy crude oil supply chains, where, part of the move towards the electrification of EVs is, to reduce our dependency on international oil supply chains, and therefore you don't want your living standards to be determined based on an overseas conflict or whether a supply chain gets cut off or gets shut off. And so there are, national security reasons for having a nutrient circular economy, because we're trying to recover and keep a lot of these critical minerals within our borders, and then we're trying to recirculate that and resell that back into the farmlands. And of course, there's not a lot of AI adoption in the wastewater treatment plant landscape. I know in the EU, there's a Darrow project with Germany. They're trying to embed AI to smartly recover resources, but not specific to nutrients. But a lot of wastewater treatment plants, they still operate off legacy systems and legacy infrastructure. And they do have a lot of data. I know Sydney Water has collected a lot of influent data. They've got different points throughout New South Wales where they do have smart meters and other nutrient collection sensors. But a lot of that data gets lost and it doesn't really get readily shared. And so there's a lot of useful data out there, but we don't ever train the ML models to improve, treatment outcomes or resource recovery outcomes. And, we have all these discussions around the use of AI and machine learning to improve productivity outcomes. That is yet to be realized. An examples, some of the other barriers include, very slow circular economy uptake of these practices across the wastewater treatment landscape. And wastewater is very complex in terms of chemical characteristics. It's not just, salt water in the ocean where it's just sodium chloride and water. You've got 13, 20, 30 different variables. You've got to factor in APIs. You've got to factor in the presence of pathogens, especially from hospitals and urinary tract infections and so on. You also need to monitor biogases and other greenhouse gas emissions. You also need to monitor the effluent output from the wastewater treatment plants to make sure that you're not damaging the environment through eutrophication. And so there's a lot of data points that go into these wastewater treatment plants, but unfortunately, not any of that is being used to train an AI or an ML model. That then gets relayed into, like, for example, an ANFIS or an ANFIS controller for nonlinear data sets to then be able to optimize the operation of the wastewater resource recovery plant. And it's great that we're seeing a lot of these acts, legislations, directives that are being pushed out in the EU. With the new AI and Cloud Development Act, with the Critical Raw Materials Act in the EU, Australia in 2023 recently declared phosphorus a strategic raw material. It's great we've got these acts, but an act alone is not going to get you anywhere if you don't have a target, if you don't have an action plan in place. And what some of these countries, some of these regional blocks are doing is that they've got pilot plans where they experiment with different technologies and then they implement whatever is the most promising for that market. It's also, we're seeing this happening in markets like India, where it's an emerging economy. It is very agriculturally driven. And so phosphorus for them is very important. That's why they've declared it a critical minerals. And so it's great that we're seeing a lot of these countries beginning to take it a lot more seriously. But again, markets like, Canada and, South America, for example, they largely, don't see phosphorus as a critical mineral. And again, with the explosion in population growth and the increased demand of the different agricultural products, fertilizer prices will continue to be volatile and will continue to increase as population growth happens. And I'll run through this quickly, but basically there are a variety of different types of AI and machine learning models. We're aware of the neural networks. We've got XGB, RF, KNN, and probabilistic neural networks, as well as SVR/FVM. And each of these machine learning models have their strengths and weaknesses on how they deal with underfitting, overfitting, whether you can supervise or unsupervise the data sets in order to train these ML models. But the main performance metrics that we want to be looking at are the root squared mean error, the R squared, as well as the mean absolute error. And that allows us to determine the accuracy performances based on the data sets that have been collected. The first publication dealt with smart cities. The why smart cities? Because in order for us to implement these AI and machine learning models, we actually need data. We need highly accurate, high fidelity data that with high integrity as well. And we need this data to be able to train the AI and machine learning models. And of course, we've got different servers, we've got different sensing layers and different, smart city layers in order for these, in order for this to work. But the starting point is we need to start collecting data. Why is it important to collect data for the nutrient circular economy? Because you're dealing with APIs, you're dealing with potential contaminants in soil separated urine, sewage sludge. We've got this portable loo lab, for example, where you're able to monitor the nutrient characteristics and profiles and determine how we should treat that waste accordingly. And basically to relay that data, whether it's inventory data or the chemical profiles and characteristics of the waste in the loo lab as an example, to the CE processor or recovering manufacturer, and then they're able to treat the product accordingly and to a high standard, or at least have it sanitized where it can be safe for human consumption. And again, I think if you're collecting wastewater with 30 to 20 different chemical variables like TSS, pH, and so on, it actually worsens the processing time and actually increases the power requirements because you're now dealing with a lot more variables. By source separating out the urine and the fecal matter, you're able to treat these waste streams independently. You're only able to look at the profile of urine. You're also able to look at the profile of fecal matter, and you're able to simplify the number of variables down from like 20 down to maybe 8 or 6 that you only need to be concerned about. So it actually simplifies the processing times when you're only looking at urine rather than urine APIs and fecal matter, as well as shower water and grey water and so on. It actually simplifies a lot of the data sets and at least the processing requirements. So it actually reduces the power requirements if you're source separating these waste streams and you're training the ML models based on these simplified data sets to maximize resource recovery outcomes. And we've already ran through resource recovery technologies, but essentially we're very interested in the diversity of products that we can recover. So it's like water, electricity, hydrogen. You can selectively recover critical minerals and metals if it's industrial wastewater. You've got thermal processes where you can recover soil amendment products, as well as NPK. And you can use biological organisms to assimilate the nutrients and reuse the biomass as nutraceuticals or animal feed, as well as recover biogas from anaerobic digestion or AD. Most countries on the planet don't have any nutrient circular economy frameworks. And again, it's great that we've declared phosphorus as a critical mineral, that there's a need to recirculate nutrients. But what is the roadmap? What is the framework? How are we going to get there? It's great we've got these recycling targets. What technology should we use? How are we going to engage the farmers, the wastewater treatment utility plants, whether they're private or publicly owned? How are we going to encourage farmers, consumers to buy nutrient-C fertilizers? What are the incentives? What are the levers? How can we drive this demand and create this self-sufficient ecosystem where through initial government intervention, you're encouraging people to adopt nutrient-CE fertilizers? Great. But what happens 10, 20, 30, 50 years down the track? Will the momentum continue to grow, to move forward? And that's basically the long-term vision, but we need a nutrient circular economy framework to recover phosphorus, to encourage everyone of these stakeholders to participate, and to set quality standards, make it safe, build trust with society, and encourage consumers to buy nutrient-C products because it's safe, it's better value for money, it's more nutritious, whatever reasons those may be. And we've launched we've embedded machine learning within the nutrient circular economy framework, and some of the valuable predictive inputs could include pH, initial TPTN, COD, VOD. You would evaluate the accuracy performances. You'd do hyperparameter tuning through grid search. You would open data share. You would basically share the data sources to society to allow startups to use the data to develop their own nutrient C platforms and software capabilities. You would have trusted digital platforms. You would have track and trace verifiable systems where you're able to track the nutrient fertilizer back to the original source of manufacturer for quality, safety, and defect tracing reasons. But essentially, it needs to be about building trust. How do we encourage consumers that nutrient CE derived produce products are far better than compared to something that uses synthetic fertilizers that have been mined from phosphate rock? And so AI and machine learning through open data sharing lays that framework, or at least gives the groundwork for a lot of this to happen. There was a publication on crafting a roadmap for Australia for nutrient C in the wastewater sector. I think we do have smart meters, but it's mostly to do with monitoring water consumption. But there are, of course, some challenges domestically within Australia that deals with the nutrient CE landscape, for example. It's not really talked about. I know we've been reapplying biosolids that have been recovered from sewage treatment plants, but again, the nutrient profile of sewage solids is a lot more lackluster compared to the nutrient CE products that can be recovered, concentrated, and distributed towards. There is still a lot of lack of awareness and education by those in the in the broader society. They're not aware that there is that phosphorus is a critical mineral, that it is in short supply. It is a volatile critical mineral, and that more needs to be done. There is still a bit of a lack of acceptance in the use of human waste on farm, especially within developing communities where the water quality that comes out of tap water, for example, creates that image that, hey, maybe I shouldn't buy a nutrient C product because I've had all these bad experiences with tap water in a developing country, of course, where the water quality standards are a bit less stringent. You want consumer support. You want the consumers to buy more. What is that motivator? So the demand isn't really there yet, as well as the lack of AI being embedded across our wastewater networks, as well as the lack of CE design in our urban spaces. And so there are some questions that we need to ask. Things like, how do we make it self-sustaining? How do we, improve the image of nutrient CE products? How do we actually get consumers and operators to get on board? What is actually stopping farmers from buying CE fertilizer products? How do we, democratize the data that can be shared across everyone so that they can use the data in order to advance, the nutrient CE goal of reaching our nutrient circularity targets? And of course there are some solutions. For example, we can drive down the cost of nutrient C products compared to synthetic alternatives. We can embed favorable microbes, or we can embed biochar that has been recovered from thermal processes when treating sewage sludge. And that allows us to amend the soil in a favorable way that it could, for example, boost crop yields by 20 or 30% if you use nutrient C fertilizers. There needs to be better education and awareness in the public and the schooling system on the benefits and the importance of recovering and reusing nutrients, and the benefits as well for farmers who purchase it, as well as having a trusted marketplace or an ecosystem or a platform where farmers can trust the safety, integrity of the nutrient C products, so that they go in, buy the nutrient C products at a wholesale and industrial scale, and then they would apply that on their farmlands, and then they would hopefully realize the benefits of improved crop yields and improved soil quality. Because one of the challenges in Australia at the moment is that our soil quality has been going down. crop productivity has actually fallen, and that has actually contributed to rising food prices across the country and across parts of the world as well. And we also need to begin to again encourage more people to come in and develop new softwares, new solutions, new technologies using the nutrient data that is publicly available. Of course, with the personal information anonymized and removed, they can use that data to advance their own nutrient CE goals. And of course, all of this is we also need to factor in the climate change impacts as well from nutrient CE. But fortunately, a lot of the emissions do not arise from the recovery process itself. Whether we're talking about pyrolysis, whether we're talking about anaerobic digestion or membrane processes and so on, a lot of it actually comes from soil application, so further downstream. So emissions that are not really directly responsible by the CE manufacturer or the seller. And so, basically, in a nutshell, is that when you apply fertilizers on soil, it leads to there is some incomplete nitrification, denitrification reactions that are happening, and then the incomplete process leads to the emission of N2O. And this paper explores the variety of strategies that are put in place in order to cut down N2O emissions. And some of these strategies include, for example, embedding biochar, using more and more struvite that you recover from urine and anaerobic digestion processes, proper sealing in AD, because AD happens in the absence of oxygen, so you're not getting N2O. It's just the leakage that is the problem, as well as for the biological processes, you could do things like identifying favorable genes, right, within the microbes or the microalgae that leads to favorable N2O reduction outcomes, as well as changing the substrates of the constructed wetland so that you're able to reduce N2O. So you want to assimilate N and ammonia as much as possible into these microorganisms. You also want to slow the N release rates into the soil so that there's better uptake of these nutrients by the plants rather than have it leak into the environment. And again, AI also needs to factor in climate change impacts. You need to be able to adjust the processes. You may, for example, design fertilizers based on different soil types. For example, soil type from geographical coordinates A may need 20% more biochar, or it may need more struvite, or may have to be purely struvite in order to fully, mitigate the N2O emissions for that area. And so there is opportunities to overcome challenges like, properly mitigating N2O, but it's already a challenge in itself because, it's very hard to accurately measure N2O emissions with existing sensors. And so having ML solutions record that data and record the emissions further downstream and being able to adjust the design of the fertilizers, the compositions in order to, provide favorable N2O mitigation outcomes. The final publication, which is the original research paper, it's the first piece of research that deals with machine learning for microalgae biomass nutrient recovery. And the four models that I've experimented with is neural network, multi-layer perceptron, multiple linear regression, RF, random forest, and XG boosted decision trees. I've manually collected more than about 4,472 data points on anything related to Chlorella vulgaris, CV, which is the microalgae species here, across 13 variables, including, like, for example, light intensity, days exposure, temperatures, and initial TNT, PPH, and so on. And I collected the data, ran a Sharp Pearson correlation matrix heat map analysis, and then based on the four models, we then did PDA, which is partial dependence analysis of plots, as well as having actual versus predicted values analysis. And then, we'll run through the results further in, but we wanted to do the analysis Sharp and predicted versus actual values analysis. As you can see, when I did the analysis with Sharp, initial TN, TP, light intensity had much more narrower, Sharp values. And basically what it says is that we were able to predict values much more consistently through initial TN, TP, light intensity, and, to some extent even temperature. But you can see up in the top with airflow, CO2, there's a lot more wider variations in SHAP values. So it was therefore a lot less consistent. And the explanation for that is that the data sets there are non-linear. When we're using XGB and RF regressor, which is mostly a linear type solving solution, that is to be expected. You can also see on the right-hand side with biomass XGB and biomass RF, actual versus predicted values, that there's a lot of accumulation or congregation of data points for biomass concentrations are lower than 1. And what that basically means is that because biomass, microalgae could also be growing at an exponential rate. So it ceases to be a linear problem, and becomes a non-linear exponential problem when your biomass is growing at an exponential rate. And so that's why there's a lot of accurate data before a biomass concentration of 1, and then it becomes a bit more scattered. But you can see it's very, very accurate in those quantities right there. And the top 2 models, the best performing model was XGB, and that had an R squared RMSE and MAE respectively of 0.98, 0.138, and 0.076. And an R squared of RMSE, R squared RMSE and MAE of 0.961, 0.186, and 0.099 for RF. And the worst performer was, unsurprisingly, it was ANN, a neural network, because it was dealing with linear data sets. We tested it anyway in order to validate, because we were under the assumption that it would predict a lot more better because of the exponential characteristics of biomass at much higher concentration levels. The average performer was multiple linear regression. That's mostly because it probably wasn't able to handle underfitting or overfitting challenges. And again, we did PDP, PDAs on RF and XGBs, and you can see pH was very non-linear. If we go back, pH was also very, according to the SHAP analysis, had a lot wider variations. As well as having days exposure. I think I would say that the PFI was highest for days exposure because of the time-based nature of this. But again, it's expected because the longer you wait, obviously, the greater your biomass concentration in that solution. Light intensity, initial TN, and initial TP were very good PFI contributors to the model's learning performance. And as a result, that has led to the strong prediction performances of XGB followed by RF. And in conclusion, what have we learned from this PhD program and piece of research work? What are some future recommendations? We know that nutrient CE is an emerging discipline. It's still under-implemented by government. It's still being discussed. It's still being white papered, strategized, and so on. There's still less targets being set on the need to recover, phosphorus within the majority parts of the world. It's still not classified by most other parts of the world, especially in countries that are very big on exporting phosphorus. Most wastewater treatment plants, they don't have AI and machine learning. They don't collect the data that is needed, and they don't share that data. So it becomes very hard to advance machine learning in nutrient CE spaces. And they would still operate on a centralized linear treatment infrastructure. There isn't a lot of CE being designed. And the future recommendations would be, having that data being shared a lot more, trusted marketplaces to sell that sell nutrient CE products to farmers. We need more studies in academia to better understand which ML models suit better based on what technologies. So again, I discussed about the 6 to 7 different types of resource recovery technologies in this presentation. We need to embed more nutrient urban CE design. So in our apartments, brand new apartments, you don't see source separated urinals at all. We need to raise awareness in education, consumers, for consumers as well as trying to retrofit existing wastewater treatment plants to recover the data that we need and to train AI models. And so that concludes the presentation right on the 30-minute mark. I'm happy to take any questions.